kind of this structure. So let's figure out how to solve it. And so the first thing we want to do, whenever we have a question, is we want to break it up into its components. The first thing we want to do after breaking up into components is to solve the reaction forces where we can. So let's solve the reaction forces real quickly. And so when there's a weight force, that goes straight away into, we'll transit to a weight force from its mass. And we can see here, this is a pin joint, this is a roller joint. So the roller joint always acts perpendicular, not always up, perpendicular to the plane itself. So it's going out to the right. And A is a pin joint. So we have AY and we have AX. I'll do that later.
Okay.
Yeah, really makes you happy.
It does.
Excellent.
Yeah.
Okay, so let's just solve what we know is really easy. When we do statics questions, we always come down to these three equations. And that is sum of the forces in the y equals 0, sum of the forces in the x equals 0, and sum of the moments equals 0. So we have to use all three of these in the end because we have three unknowns and we need three equations. Let's start with the first one. Sum of the forces in the y is 0. AY is equal to, well, just whatever's going down. So 400 times 9.8, which is 3920. And that's really cool. But we still need to find the other two. So let's do sum of the moments. And the way I want to take moments is any place in which I can reduce the number of moments in my equation. So whenever there's a 0 point, so I'm just going to take this point here. I'm going to take sum of the moments at A equals 0 because it's a statics question. And so anything going clockwise, anything going anti-clockwise. So this 400 kilo weight here has a distance of 5. So let's do that. 3920 times 5. And resisting it is this force D here. And that's going in a counterclockwise direction. So I'm going to write it on the other side of my equal sign. And so that's D times what's its perpendicular distance? It's this distance here. So it's always the perpendicular distance. So that's what we're looking for. It's 5.5. D is going to be 4.31. Sorry, any questions? Yes.
Are we taking G as 9.81 or 9? Because, sorry, 9.81 or 9.8 because the values are different by 4. Yeah.
Take 9.81. I think we're gals been taking 9.81.
Okay, so the AY will be 3924.
3924. Okay.
It's 5.
There'll be rounding errors. So yes.
The distance is 5 meters.
This is 5 meters. 3, 2. Excellent. That makes it better. So that means this is the same number.
Yeah.
Cool. That throws off all my numbers.
Wait, how come the radius of the frequent counter? Like,
excellent point. That is where the radius is counted. So this distance is 5. And we want this distance here. So that includes up to here. And because the radius is, this just means r is 0.5. So we have 0.5 here. So 3 plus 2 plus 5.5. So this is actually 5.5. I missed that. Thank you for pointing that out. And so that means when we do the calculations, now we get an answer of 4.31. 4310. Like that. And then we can do our last equation. Sum of the force in the x direction equals 0. D plus AX equals 0. So AX equals minus. And so what does that just mean? That means I made my assumption wrong. So I'm just going to switch the direction, making it go to the left. And for good practice, let's write all our values on the diagram. So this is 4.31, rounded, obviously. This one here is 3.92. This one here is 3.92 and 4.31. Okay, so now let's start disassembling our structures. So we can see here that we have three structures. We have AD, this curved one, and this BF. So let's kind of just draw them like this, and we'll draw them individually. And how do I draw this one? like that. A, D, C, E, F, E, and B. And so whenever we disassemble a number, we still have the original reaction points. So at A, there's still the 3.92, and this was 4.31. So I think 2 decimal places is a good number of decimal places. D still has this reaction here, 4.31. And when we disassemble this structure, we expose the internal reactions at those points that we disassembled. And so at B, we introduce By and Bx. At C, we introduce Cy and Cx. Cool. And interestingly, when we introduce our By and Bx, on the alternate diagram, the forces are in the opposite direction. So on this, it doesn't really matter which one's going up, which one's going down, as long as you keep them opposite. So now in my other diagram, By is now going down, Bx is now going to the left. Same with this one here. Dy, Cx. And then with the E, we can draw E as well. So E, Y, Ex. And then at E, again, opposite direction. EY, EX. So we end up with 3 diagrams, which we need to solve to solve the question, right? We need to solve all these things. The last thing we need to remember is the F here. So at F, we can, I'll just draw another little diagram. Oh, we could just draw it on. At F, I know, we'll draw another diagram. So at this pulley, we see that there's this tension force here going down. And there's also this tension force on the other side, because tension is constant throughout the whole thing. And so that means there's a reaction force at F resisting the weight force pushing it down, and resisting this force to the left here, holding the weight up. So F, if we just analyze the pulley, I'll draw a little diagram here, which I keep saying I'll do. We have tension down, and then F is basically a pin joint. So F is got some resisting Fy, Fx. And so let's start with the simplest diagram, which is in fact this pulley diagram here. I can see that, well, Fy just equals T, Fx just equals T, which I kind of mentioned before, is 3.92. And so that means when I come back to drawing this diagram, which I didn't quite finish, remember that our values have to be in opposite directions. So Fy, Fx, and I know the values now because I calculated in this first diagram. So Fy is going to be 3.92, Fx is going to be 3.92. So let's go about kind of solving these equations now. And so I can use my 3 equations as I had before. I can use moments, I can use some of the forces, and I can use some of the forces in the x and some of the forces in the y. And so I always want to pick the easiest diagram possible. And if a diagram has 3 unknowns, it means it's solvable. If it has more than 3 unknowns, it's not quite solvable yet. So looking at our 3 diagrams, we can see, well, this is 1, 2, 3, 4. It's got 4 unknowns, so we can't quite solve it yet. This one's got 1, 2, 3, 4. This one's also got 4 unknowns, so we can't quite solve this one. 1, 2, 3, 4. This one's also got 4. So we're not off to a good start, but fortunately, we can do some manipulation. And so let's look at this equation here, because this one's probably the most simple. We can see that Cx and Ex are opposites, and Cy and Ey are also opposites. And so as I'm solving this, I want to mark that on my diagram. So let's convert either all the E's into C's or all the C's into E's, and see that makes it easier. So I'm just going to convert this one into EY and this one into EX. Okay, and then hopefully this makes things easier to solve. So now let's look at this diagram. Well, we can kind of solve it. Let's just try and solve it anyway. Even though there's 4 unknowns, we can still solve some of the unknowns. So let's take moments at any point. And so the way I want to take moments is, again, a point in which makes the most unknown forces disappear. So if I take a moment at this point C, what do my answers do? If I take moments at this point B here, then it makes it really good because anything vertical I can just ignore because it has a distance of 0. So now I can ignore by, bx, and this 3.92. So I'm going to move this diagram. And let's solve. So if I take the moments at B, I get sorry, EX. Oops, I didn't leave enough space. So sum of the forces equals 0, and then we get this equation here. Right on. So what do we do here? Yeah, so we get an answer for EX, which I think is 13.06, if that's correct. Yeah, I'm going to pretend that is. Yep.
Where did you get 3.92 times 0.5?
All right, let's put the distances on. So 1.50. Oh, sorry.
What is the force? Like, what is the...
We missed. There's also coming out of. I'll do it in a different color. We have to include this point here. So when we analyze it, yes, we do cut everything, but there's still this tension force pulling against it. Yeah. So let's draw that on as well. There's this tension force, which is 3.92. So this is a distance of 2, 1.5, 1.5. So that's how we get our numbers. This is times 3. I think we have to move.
Yes. Yeah. Sorry. Can we all move to the air, please? Yeah. Sorry, that's on the ground. At the end of the corridor.
Let's keep going through where we're up to. So yeah, we're able to find EX. However, let's look at something over here. So looking at this diagram now, we can see that CX and CY, they must equal each other. And so that means CX can be represented as a force like this, and EY, so E can represent it as a force like this. And they have to travel through each other, which means we can figure out what angle they have to exist at just by looking at this diagram. So looking at this diagram, I can see that tan theta equals cx on, cy on cx. But tan theta also equals, well, this is 1.5 meters and this is 3 meters. So tan also equals 1.5 on 3. And so that means I know that equating these two equations together is that cy is equal to half of cx. And likewise goes for ex. And so using this information, let's keep going from what we did down below. So we found ex, and I said that cy equals half cx. So I can find that cx is also equal to 13.06. And cy is half of this, so cy is equal to 6.53. And ey is equal to cy, so that is also equal to 6.53. And so what I've done now is I found this one, so I'm going to update my diagram. This is 13.06. Ey is now 6.53. And looking at this diagram, I only have two unknowns now, which is bx and by. So if we do sum of the forces in the x direction equals 0, and sum of the forces in the y direction equals 0. We can go through and write out all the forces, but I think for time's sake, I might just jump ahead. So you should get, in this one, bx equaling 9.14 and by equaling 2.61. And so, yeah, I can upload all the answers as well if you want to see a thorough breakdown of some of the forces. But I think we've had enough practice with that, so I'm going to keep that just like that. And so let's see, have we solved everything we need to solve? B, yes. E, we found. F, we found. E, we found. C, we found. So happy days. That one's done. That's question 1. Any concerns with that so far? Cool. Let's move on to the next one then. Okay, so the next one here is question 2. And let's see how this one goes. So we have a block of 7 kilos and 10 kilos, and they have some sort of friction values. Okay, so in this question, there's a few things going on. So we're trying to pull P, and there's a friction force between the ground here. And so friction force always resists the motion. So if we're trying to move to the right, friction force is going to move to the left. And if we're trying to push it to the left, then friction force will move to the right. But since we know we're trying to pull it to the right, we know friction force is going to be equal to this, right? The coefficient of friction times the normal force, in which case is 0.3. And so I might add that the friction force is acting along this plane, like along this connected surface. 0.3 N in A. And then there's another friction force acting here, which is 0.4 in B. Okay. So let's start drawing our free body diagrams. So there's a tension force here, which is just keeping the block from moving. And this block here has a weight force. So A has a weight force of 7 times 9.81. And B has a weight force of 10. Okay, so So let's do that. So we can figure out, well, what is the what are we trying to figure out? So we're trying to see how far we can pull P before it starts to slide. And so let's look at the resisting forces. So we have 0.3. So let's do some of the forces. Some of the forces. Yes. Okay. So let's look at B first. So let's just look at block B. So let's draw a diagram of just block B. So we have this block B. We have this T force. We have this weight force. And then we also have this friction force. So which direction is the friction moving? So because the ground under is trying to move to the right, the friction force is going, which was left? No. Sorry, we have to think about it. Yeah, it's going to the right. So how can we explain this? Relatively speaking, the block B, if the ground is moving to the right, block B itself is moving to the left. And so that means if block B is trying to move to the left relative to the ground, friction is trying to resist this force. So friction actually goes to the right on this block, which is a force of NB times 0.4. And we know the normal force, which is above. So the normal force is just going to be 10 times 9.81. And so we can figure out the tension in the string of block B using some of the forces in the x direction. So that is T equals 0.4 times NB, which we found was to be 98.1. So this tension force here is equal to 39.24, which is all cool. So let's look at, I'll leave that there. So now we're also going to look at block A. And so block A itself has its weight force, 7 times 9.81. It has this P force, which is we're trying to figure out. It has the friction force from the ground and the block, which we talked about, times the normal force. And so I'll make this NB because it's a different normal force. And of course, every object has a normal reaction force, N. So I might need more room now. But there's also acting up on the block is there's a reaction force of B acting onto A. So there's a normal force of the total normal force plus the normal force of B, opposite equal reaction kind of thing, acting at B. And from B, as I talked about before, there's a friction between A and B trying to resist. So that's 0.4 NB. Right, basically this force.
Can you explain why is there NB going down?
Why is it going down?
Yeah.
This is basically the weight force of B itself.
Oh yeah, because it's coming right.
Yeah.
That makes sense.
Okay. Cool. So now let's solve this diagram. We know what NB is. That's 98.1. So now let's figure out what N is. So N, using some of the forces in the y direction, equals 0. N equals, well, just the two forces going down, right? 7 times 9.81 plus 98.1. And then now we can use some of the forces in the y direction. We have P. What's resisting it? We have this force here and this force here. Which is All right, I'm just gonna whatever. All right, I'll just jump to the final answer. You can figure them out yourself. 86.7. No. 66.7. 89.2 is what I think it should be.
Okay.
Yes, 89.2. Yes, so this should be 68.67, and then using this number, and this number, this number here, 89.2. Okay, which is cool.
It should be 166.77 and it should be. When we create fy equals to 0 and then we find the normal
Oh, sorry.
using that one, shouldn't it be 160?
So 68.67 plus 98.1, which gives us 166.77. There we go. Okay. And so then this is 0.4 times 98.1 plus 0.3 times 98.1, which gives us this. Like that. All right. I think those numbers are right now. And so that's cool, right? So if I pull it at 89 newtons, this thing's going to move. However, there's other things that could happen instead. Oh, sorry. This is, that one's right. This one's wrong. This one is 166. Cool, like that.
Minimum 2 weeks.
Sorry. However, no, I think it's all right. Okay, cool. Let's move on to the next one now. Hopefully you would have copied that down in time. Okay. Okay, so for this question, we have to remember a few things. That is the angular displacement. So these are the, I guess, the rectangular coordinates, and then these are the angular values. So angular displacement, angular velocity, and angular acceleration. And that's equal to, just timesing it by the radius itself. And so the radius is going to be this lever arm here. Right? We can see that. So we want to figure out, as B moves, how does A move? Also, how does AB move? Okay, so let's just look at B itself. So when OB rotates, OB is moving at a constant angular velocity W. So that means, let's just write that down. The angular velocity for B is, we'll just call it B. And the velocity of B itself, that is B, the point itself moving in time, is going to be, well, what did I have here? Velocity times, angular velocity times the radius, so WR. And we want to find the velocity of A, so we can find that the angular acceleration of A is what we need to find in the end. But we need to find the velocity, in order to find what we need to find the velocity of A itself. And so if you remember, this formula is the relative velocity formula, and that is the velocity of A is equal to the velocity of B plus the velocity of A relative to B. And so what does that look like on a diagram? Well, the velocity of A itself is just straight up, right? It has to go straight up along this item. And the velocity of B, the velocity of A relative to B is the rotation itself. So as B rotates across, A has to rotate, well, because it's a stiff thing, it has to rotate in line, it has to rotate in circular motion. So the velocity of A relative to B is in circular motion. Okay, so yeah, let's have a look at that. So the velocity of A relative to B is equal to this AB block moving in circular motion. And what's the formula for circular motion? It's equal to this, right? This formula here, WR. And so yeah, so that's equal to the velocity, angular velocity of AB, which we don't really know, times the radius, which is R root 2. So let's switch out of this color. Yeah, just by this length here, R root 2. Okay, and then, so now we need to figure out the angular velocity of A relative to B. And this is equal to yeah, and this is going to be also equal to the given radius itself, because as B rotates, A has to rotate in the same manner in order to equalize.
Is B the instant center? That
B is the center.
is B the instant center? I'm not sure. Like, why is the omega the same?
Um,
One will be opposite and one will be like the other will be opposite of the first one, right? Because it's a cancel.
yes, yes. So yes, it will be opposite, but same in magnitude, if that makes sense. Yeah, same in magnitude. Yeah, okay, cool. Yeah. And so now that we've established let's keep going forward. So right, so the angular velocity of B itself is omega, and because it's moving at a constant velocity, the angular velocity is also constant. So that means angular velocity of B is 0, and a follow-on effect, the angular velocity of, the angular acceleration is 0. So the angular acceleration looks like this, which equals 0. So our end goal here is we're trying to find, well, what is the net acceleration of B? So remember that acceleration is equal to the acceleration in the tangential direction plus in the normal direction. So this one here is your standard B squared on R kind of equation. And this one is, well, 0, because it's moving in a constant direction. And so for B, the acceleration of B itself is just going to be AT, which is 0, plus the centripetal acceleration, which is V squared on R. V squared we established was W squared R squared on R, so W squared R. Oops, kind of like that. And so what we want to find is the angular acceleration, which is equal to the acceleration divided by the radius. So we can find the acceleration of A, which is equal to the acceleration of B plus the acceleration of A relative to B. We can kind of solve our answer. So this is the last step that we need to get to. So let's push this down. And so we found this one already, which is equal to just W squared R. But the acceleration of A relative to B also has its components in the tangential direction plus relative to B in the centripetal direction. N. T. Okay, so that's no good. All right, so we need to find the acceleration in the tangential direction and acceleration in the normal direction. And to go back to our diagram, we can see that A itself is moving in a straight line. So it's moving directly up. And so all right, okay. So because the net acceleration, right, acceleration of A net is directly up, let's draw on the tangential acceleration. So the tangential acceleration is this way, and the net acceleration, the centripetal acceleration at this point is up the up towards the anchor point. And so at this point, we know that the acceleration net is equal to the acceleration n plus acceleration t as a vector, right? So it's going to be that means we know the angles of both of these. So this is 45 degrees, and this is also 45 degrees. And so AN, taking some of the forces in the y direction equals 0. Oh, sorry. Some of the forces in the x direction equals 0. We have AN cos 45 equals AT cos 45. So AN equals AT. And so that means So A net is actually going to be equal to 2 of the acceleration in the tangential direction, or probably what's easier to find, in the net direction. Oops. And so coming back down here, we know that the acceleration in the relative direction is equal to v squared on r. And we know that v squared is wr squared, and the radius is, well, the radius is ab, so that's going to be root 2. So r root 2 squared on r root 2. And that's going to net to be omega squared r root 2. So that's in the tangential direction. And so in both the tangential directions and the normal direction, it's going to be omega squared r root 2, right, using v squared on r. And so now that we want the angular acceleration, is just going to equal a net on AR, which is going to be
Sorry to interrupt.
Yeah. Yeah.
Why did AB tangential and AB radial become the same value? How did that happen?
Because when we're up here, we could see that one's going up to the left, top left, and one's going up to the top right. And so we know that the net has to be vertically up.
Yeah, just the velocity is up.
Yeah. So that means the sum of the acceleration in the x direction has to be equal to 0. Because it can't accelerate to the left or right. It has to go straight up.
Oh, right. Yeah.
So that means these two end up equating to each other because they're acting.
Their components are.
Yeah, their components, their horizontal components are equal. So that means their whole components have to be equal, just in different directions. Yeah. And then, yeah. And so now when we take their components, right, because we're looking at vectors, they end up canceling each other out. To get omega squared. So it should be omega squared in the end. Henry, do I have time to go through a frame? Okay. The last question I'm going to go through is this frame question here. And so this is from the 2021 final. If anyone wants to see it, take like a copy of the question. So let me. Okay, so let's look at this frames question now. Right, so this one we have to first calculate the reactions. And so when looking at the different types of reactions, this here is a fixed joint. And so fixed joints have not only an X and Y, but they also have a moment reaction. And so as we solve this, let's convert our UDL into a point load acting straight down the middle. So 4 times 5, which equals to 20. And P value of, let's just do P equals 10. And so if we do sum of the forces in the y direction, we have AY going up, we have 20 going down, and we have this P value here going up. So we have 30. Cool. And then sum of the forces in the x direction equals 0, AX equals 0, because there's nothing in the x direction. And then finally, we have to solve for the moment. So we do sum of the moments in the A direction at A. We have our UDL acting 20 kilonewtons straight down the middle, so times 2.5, plus P, which is 10, times 3 meters, equals MA. And so because MA is going in a different direction, we get a different answer. It's going to be positive. So MA is going to be 80. Cool. So let's look into drawing the shear force, axial force, and bending moment diagrams now. And so the way we do this is we have to remember our convention. So this convention is what we always use. And this is like our positive values. Oops. And so these are going to give us our moment, axial, and shear positive values. And so if we cut from the left, so if we cut and kick away the right and only analyze the left, we expose the right end of the structure, and so we always use this one. However, if we cut the left side away and expose this left end, then we use this as our positive convention. And so the way I'm going to do it, it doesn't really matter which one you pick as long as you're consistent. And so the way we do it is we always start from one point of our frame and we work our way around to get to the end. And so I'm just going to start from point A because that's kind of makes sense. And I'm going to draw a section of the frame to analyze. So I'm going to analyze this point from A to B. And so, yeah, I'm going to draw my frame. Cool. So let's just draw it on. So we have this AY, which is equal to 30. And we have this moment here, M, which is equal to 80. And so because I'm going to cut it somewhere before this joint, so I'm going to cut it somewhere along A to B. Guys, if you're going to be chatting, can you leave? If you're going to be chatting, can you leave? Cheers. Yeah, so we're going to pick a point somewhere along this frame of A to B. And let's just call it X, right? So if X equals, let's look at our diagram. If X equals 5, then what we're going to do is we're going to find the values at B. If X equals 2, we're going to find the values at this 2 meter mark. And so that's what we're going to use. We're going to use X. So when we cut it, we're going to expose our joints. And I'm going to choose this as our standard convention. So that means I'm going to expose the internal reactions. So N, the internal reaction of the axial side, the internal shear, which is going this way, and then the moments, which is going this way. So the diagram is just rotated 90 degrees there. Yeah. We're exposing just before B. Just before B.
One question I was having is, do we not consider AX?
Well, AX is 0.
Oh, that we already.
So we already figured that out. Yeah. So AX equals 0. So now we have this diagram, and we just need to solve it. So let's solve it. Sum of the forces in the y direction equals 0. We have N plus AY equals 30. Sorry, equals 0. And so N equals minus 30. So that means our axial force is negative. Let's do our x direction. There's no forces in the x direction. So V equals 0. And then doing some of the moments at A, at this point here, some of the moments is equal to, well, it's just going to be equal to M. And because they're going in the same direction, we have M plus 80 equals 0. So M equals minus 80. And so these are our values for any point along A to B. If, yeah, so N is minus 30, M is minus 80, and V is 0 for any point. And so this probably seems a little bit trivial, but as we go along to the next section, it'll make sense. So now the next thing I want to analyze is I want to analyze this section here, B to C. And so when I analyze B to C, I can't make 2 cuts. So I can't make 2 cuts and analyze just the top. I can only make 1 cut. So I'm going to make a cut somewhere here, just before C again. So what does that look like in my diagram? Well, because I only cut C and disregarded the rest of C, I still have to draw an A. So A has this 30 and this moment. And then we go up 5 meters. For some value of X. So where this is B to C. And at along the top, we have this UDL. And we can represent this UDL as equal to a point load, which is 4 times its distance. Right, so 4 times X, and this point occurs X on 2 away. And so again, I'm going to draw on my internal reaction forces, which is N, V, and M. And then I'm going to solve this diagram as a whole. So again, sum of the forces in the x direction equals 0. Well, there's no forces in the x direction, so actually N just equals 0. Sum of the forces in the y direction equals 0. We have 30 going up. And what do we have going down? We have V, and we have this 4x going down. So V plus 4x going down. So that means our shear force, which is equal to V, is 30 minus 4x. And what does that mean? So that means if I wanted to find the shear force, let's look at our diagram. V equals 30 minus 4x. If I wanted to find the shear force at, say, B, well, this is a distance x away from B. So that means the shear force at B is going to equal to 30. If I wanted to find the shear force in the middle, then I'd say, well, x is going to be 2.5. And so, yeah, x. X is 2.5, and so that's just going to give us 20, I think. Again, if x is at the end, then V equals 10. So we found an equation that will find the shear force for any point along this graph, along B to C. And then we do the same thing with the moments. Sum of the moments equals 0. We have M plus MA, which is 80, equals, plus x onto times x times 4x. Sorry, that's the distance. So again, if I wanted to find a formula, I just had to put in a number and the answer will come out. So M is equal to minus 80 minus 2x squared. Which I think is not right. I think it should be plus. Oh, sorry. We also forgot about this point here, which is 30. Right, so this 30 has a distance of 30 times x, right, for some distance x, whether that be 0 all the way to 4 meters. So we end up with this equation. So that's minus m equals 30x minus 80 minus 2x squared. So now we've gone A to B, B to C. Next up is C to D. So let's do C to D. Again, we're going to cut right before D and draw everything else up until that point. So $4x. This is 5. This is 5. And then we have our 30 and our moments, which is 80. So again, we draw on the reactions, the internal moments, internal reactions. So there's N, V, and M. So notice that although the direction of N has rotated, V and M always stay consistent in its relative positioning. If you change the relative position, you get a different answer. So now that we have all the points, let's solve it again. Sum of the forces in the x direction equals 0, V equals 0. Sum of the forces in the y direction equals 0. We have 30 up, we have N going down, and we have this UDL going down. So we get N equals 10, and sum of the moments equals 0. We have M plus 80 plus this 20 times 2.5 minus this point here. So this is the UDL. And then the reaction force as well, don't forget that one. That's 30 times 5. And so we're going to get some number. I think the number here is going to be m equals to 20, like that. And so now we're almost done. We'll do the last part, which is D to E.
Like, if you flip the directions of N and V, like, how did you know that the V is going like this and the N is going down?
So the N always goes out of the where I cut it. And then using this diagram, I always have to keep it the same. So I can rotate this diagram 90 degrees, and notice that V is always clockwise to N. So if N is going up, V is clockwise to V is clockwise. If N is now going to the right in the next diagram, V is now still clockwise. And then this last one, N is going down and V stays going clockwise. But if we go from the opposite direction, then we have to swap everything. Yeah. So this last section we can do in two ways. We can either go all the way around again, like this, whereas we have our UDL, which is 4, and then we have our internal loads, N, V, M. Another method is we can go from the opposite end. So instead of cutting right before E, I can cut right before D and analyze the other half instead. This may be a little bit confusing, so if you get confused, don't worry, but I'll draw it on anyway. We can analyze the other side, which is P. And if we do analyze from the other side, we have to make sure that everything is in the opposite direction. So N is now going to the right, V is going down. Is that right? Yeah. And M is going in the other direction. So this may cause for a simpler calculation, but you're more likely to make an error. So I wouldn't recommend against doing this and just keeping the same pattern all the way through. And so again, let's just solve these things here. We have sum of the forces in the x direction equals 0, n equals 0. We have V equals sum of the forces in the y. V equals V plus 30 equals 20. So V is minus 10. And then sum of the moments. And so the important part of this moment section is that the moment's at 2.5 meters away. However, the position of our moment is variable, right? It's this distance x here. So this distance here from the middle of our UDL to where we're trying to analyze is going to be 2.5 minus x. So equals, oh, sorry, not equals. Minus 20 times 2.5 minus x equals 0. We'll get an answer. M equals, oh, so this should be plus. And I think I missed one. Right, sorry, this point here as well, the reaction point, which is 5 minus x. So if we simplify this, I think we should get 150 . which is 20 minus 10x. Let's just say that 20 minus 10x. So now putting that all together, we can draw on our 3 diagrams that we need to draw. So let's just draw them. So let's look at the AFC now. We have to go through each one and figure out what the equations were. So we're looking for n. So n is minus 30 at the start. Then along the top here, n is 0. Then C to D, n is 10. And then at the very bottom, n is 0. So let's draw that. I already forgot what I said. I don't know, I think this is 30. There's 0 at the top. And then it becomes minus 10. Like that. A, B, C, D. Now let's do the shear force diagram. So along A to B, shear force is 0. Along B to C, it follows this equation here, 30 minus 4x for that distance. C to D, V is 0. And then we have minus 10 for the last part. So I already forgot what that was. So that's minus 10. 30 minus 4x. So when x equals 0, it should be 30. Because this is 5, when x equals 5, v equals 30 minus 4x. And so it follows this equation. Because this distance is 5, it finishes at 10.
Could you explain the sign conventions of this? When is it up? When is it down? And like how do we do the sign conventions?
The sign conventions don't matter. So generally, we do outside is positive, inside is negative. Inside the frame, yeah. And then for the bending moment diagram, we have a multitude of equations. AB is minus 80. Okay, that one's not too hard. So let's draw on minus 80. And then from B to C, it follows this equation, this one here. So how do we plot this point here? No one really knows. X equals 0, we have a value of minus 80. X equals 5, I think we get a value of 20. And then it's some sort of parabola. Like that. Doing the next one. C to D. It's just a value of 20. So that one's positive. The way you know you've done something right is if your corners, they should have the same value. So in this corner here, it's both minus 80 on either end, so that's good. On C here, they're both positive 20, so that's good. And then my last one is 20 minus 10x. So that looks like this. Again, 20 and 20, I've done something right. A, B, C, D, E. So that's how we do the bending moment diagrams and shear force diagrams in frames. Yep. So this is AFD as well. Okay. Yeah.